Okay, number 1 says you should be able to list the 5 main elements of natural selection. So Darwin's theory had kind of 5 main parts to it. Who can find it in their notes? Because I'm sure you don't remember.
Population has variation.
Okay, populations have variation. So when we look at organisms in a population, they look similar, but they do not all look the same. Now, sometimes those variations can be slight, enough that, just by looking at them, you would not be able to tell. But by crucial measurements, we can see there's going to be variation because organisms don't all have the exact same genes, unless you're an identical twin. Yes. Okay, so populations have variation. What else? Not all live to reproduce. Life is hard. There's going to be some that die. Okay. What else? What? What's that?
Okay, so like not all live to reproduce. But not like groups that have a lot of kids, like whatever at once.
Sometimes, but even in species where they may have only a couple of offspring and put more care into them, not all those are going to survive to be able to reproduce. I mean, not all organisms are going to pass their genes on. That's the point. Okay? So there's variation. Not all organisms are going to be able to pass their genes on. What else? Okay, the environment tends to be bigger than, or the number of offspring produced tends to be bigger than the environment can actually hold. That means there is a struggle for survival. Life is a battle. And the organisms that are going to fit into the environment best are the ones that are going to win. And by win, what do you mean? Pass your genes on. That's winning in life. Okay? So, I think I kind of hit the 4th one, right? Right, so that's kind of the 4th point. And then what's the last one? Because the organisms that are more likely to survive have traits that fit into the environment better, in the subsequent generations, we should see more of those actual traits. Okay? Think about all those computer simulations that we did. Peppered moss. The black ones were more likely to survive in the sooty environment because they were able to hide. So in the next generation, more black moss were born, and that just kept going until most of the population was black moss. Okay? Remember, that's evolution. We saw evolution because we saw a change in the overall population. It's a small change. We can see big changes over long periods of time, but any change in a population would be evolution. Okay, any questions there? Would be a good idea to know those. Those are an important part of this entire theory and the stuff we're going to talk about over the next few chapters. Okay, number 2 says explain how artificial or directed selection in domesticated species can be used to draw parallels to natural selection. What would be an example of artificial selection?
Breeding dogs.
Breeding dogs, right. You want a dog with a certain type of ears, really long, floppy ears. So what are you going to do?
Get the floppiest dog together.
Right, we get the 2 dogs. Obviously, we need males and females since we're talking about dogs. So we get the 2 male and female dogs that have the floppiest ears. We put them together, and we keep doing that over generations until we have the floppiest ears dogs that we see. Okay. Now, because we are so specific, artificial selection can occur much quicker than natural selection. Okay, because we're not even going to let those other dogs breed because we don't want those floppy-eared dogs. So we're not going to let them breed at all. Whereas in the wild, some of the ones that may not fit in the environment quite as well may still pass some genes.
Yes, come towards Jacob's bird. Jacob, put your foot
Okay.
Go to Cali. Go to Cali. Yes.
From here.
I want to stick your hand out. Stick your hand out.
If you want to spend the rest of the time looking at a spider instead of talking about what's going to be on the test, that's fine. I'll skin off my back. Okay.
Seriously.
So, artificial selection is much quicker, but it works based on the same principles. Organisms are going to pass on traits based on the traits that they have. The offspring will look like that. Depending on which ones are able to reproduce those, that's what the population is going to look more like in the next generation.
So to draw parallels, just kind of like how they're saying.
Right. Okay, number 3 says explain how natural selection may affect a specific trait in a population. So this would be more like a kind of a specific example. If I said that you had an environment where there was lots of green bugs and a few blue bugs in this population, and it was, in a grassy green environment, and then some disease comes through and it turns all the grass blue. What would we expect to happen over time?
The green bugs would die.
Not only that the green bugs would die, but what else?
The blue would thrive.
That the blue would thrive. They'd be more likely to pass their genes on and survive. And that what we would see over time is that the population of bugs would be more blue than green. Okay, so that's the kind of example that you need to know for like number 3. So depending on the situation, you should be able to kind of think about how the environment will affect a specific trait. Okay, number 4 says explain the populations evolve over time. Well, individuals are either selected for or against. Remember, individuals themselves cannot change. Giraffes don't stretch their necks. Either you have a long neck and you can eat and reproduce, or you have a short neck and you starve to death. You don't pass your genes.
Can't they just use bushes? Usually if you...
Depends on the environment. If there's no bushes around, that's the point. So giraffes probably evolved their long neck. The populations did in an area where there were no bushes. There were no low stuff to eat. They had to eat the tall stuff, and so the tallest ones were the ones that passed their genes. Yes. Okay. All right. And so that kind of goes along with number 5. Contrast Darwin's theory of evolution by natural selection with Lamarck's theory of evolution by use. And that's what I just talked about, right? You can't change yourself. You have the genes that you have, the traits that you have. That's how you're going to fit into the environment. Well, listen, when we say you can't train yourself, we're kind of putting ourselves into a natural population. Humans kind of go beyond all of this because of our technology. Okay, number 6 says explain adaptation and heritability of traits and how they fit into natural selection. Remember, in this case, an adaptation, we're talking adaptation as a noun, not a verb. An adaptation is just a trait that helps you fit into the environment. So blue color, if there's a blue environment, that would be an adaptation. Our thumbs are adaptations. They help us do certain things and live and fit into our environments. Polar bears have a hollow fur that helps insulate them. That's an adaptation. The actual hair itself, there's nothing on the inside. It's just the way it's made. So it's kind of a hollow cone, and so because it's hollow on the inside, it's like a thermos. It doesn't let heat in and out very easily. It's like an ice cream cone with a kind of like an ice cream cone, yes. It's a no ice cream. Okay. Now remember, something that is an adaptation for an organism, if the environment changes, may cease to be an adaptation. It may actually not help that organism out anymore. So having that hollow fur, if the earthworm's up too much, if polar bears are too insulated, keeping too much of that heat in, that may not help them out very well. It will cease to be an adaptation.
So then what would you call it?
A detriment. It's actually hurting their survivability. That's vestigial. It doesn't really hurt us. It doesn't affect your ability to reproduce by getting goosebumps.
I think wisdom teeth are kind of a...
Wisdom
They
teeth.
could kill people because you
Yeah.
can't infect them.
Wisdom teeth definitely could be. That could be a detriment because they infect. Yeah, they can get infected and impacted, and that could cause you to die. Nowadays, it's not so much because we have the technology to rip them out of our skulls.
Don't let her answer, guys.
Okay. Number 7 says, describe some of the evidence of evolution, including the fossil record, homologous structures, vestigial structures, DNA sequencing, and embryology. So, the fossil record, remember there's lots of different organisms where we don't really have complete fossil records, but there are some examples where we do. We talked about whales, we talked about elephants, we talked about camels. So there we can see actual lineages back through the ages of fossils and how those fossils change because those organisms were in changing environments. Funky? Okay.
What lineage did you show us that we didn't have?
Oh, the camel. Yeah. Literally just said that.
So basically, the answer to this question is like, we have records of some animals.
Right, we have of some organisms, we have good fossil records that show their change over time. Okay, homologous structures. So remember, that's the shared evolutionary thing. We talked about how if we look at mammals, bats, and whales, and humans, even though we have much different appendages, when we look at the actual bone structures, we have the same basic number of bones there. So that shows that there is kind of a commonality to those structures, even though they're different in some ways, they're also similar in some ways because of that common ancestor. And we talked about the deer and the moose horn. Mammals all produce milk, right? That is a common trait. So that would be a homologous structure, the mammary glands that produce the milk for the offspring. It shows that commonality, that common evolutionary link.
So from the longest you could put all males produce milk.
That would be an example of homologous structure.
Yes.
Generally, the females, it is possible for male mammary glands to work. Usually, they're not too common. Okay, vestigial structures. Vestigial structures are things that are kind of leftovers from evolutionary change. The organism changed in some way because of its environment, but it didn't change completely so that there's some leftover thing. We talked about in humans, appendix, tailbone, wisdom teeth. Talked about male legs. Yeah. Some pythons have little nubs on the back where their legs are. Okay. But make sure you realize, right? It's not like any of those actual pythons ever had legs themselves, but it's evolutionary leftover. Back in their history, organisms that they evolved from had legs, and as those legs got smaller and reduced, they just didn't completely disappear. Okay, DNA sequencing. So that's basically just the idea that when you take organisms and you compare their DNA, you can see how closely related they are. Organisms that are more related, species that are more closely related, are going to share more DNA than those that are not as closely related. We share 97% of our DNA with chimpanzees. 97% of our DNA is exactly the same as chimpanzee. So the differences that you see between, say, Casey and a chimpanzee
Or 4%.
3%. 7.
Sorry. I said
Now, if you were to, say, compare our DNA to an orangutan, farther away, our DNA is not going to be as similar. Well, I mean, yes, you and Bryce look more, close to each other, but as far as any other organism on the face of the planet, probably the closest.
So humans and humans share like 99% DNA.
Oh yeah, well 99.99.
So there's only 0.1% of DNA that's different, and it makes us all completely different.
Absolutely.
That's so dumb. That's so dumb.
Sure, there's a lot of genes though. That shows us how many actual genes there are. How much of our DNA there actually is, so that there can be that small of a difference that we can still see how it changes. I mean, that still could be literally millions of genes that are different. It's just a small percentage because there's so many genes. Okay? And then embryology. So we talked about that on the last question. Just the idea that when you compare organisms, when they first start out, the embryos, we're looking at vertebrates, but the embryos all look very similar because we kind of start out in the same place, and then the changes that happen over our development affect whether we turn into a toad or a human or whatever. And it is thought, probably shouldn't bring this up because lots of questions, we still have stuff. But it is thought that we could maybe take birds, which we know are descended from dinosaurs, and by taking a chicken and switching off some of the genes, we could get something that looks more like an actual dinosaur. That is something that there are a couple scientists that are suggesting. It's called de-evolving. We're not changing any of the genes, like some of them. We're just turning some of them off so that the ones that make it a chicken aren't expressed, and the ones that are left over from the dino days.
I want a dinosaur.
I know. You don't want to pet one of them?
You could train it though if it never knew anything.
Okay.
You can train a chimpanzee.
Quickly, we have 10 minutes. Number 8 says we should be able to describe the different models of the rate of evolution. So here we talked about gradualism and punctuated equilibrium. We should be able to talk about the differences between those. So gradualism, as the name implies, is kind of small changes over a long period of time. So you can think about it like walking up a long, but not particularly steep hill to get to the top of something. Punctuated equilibrium would be much more like walking over a flat piece of ground to get up to something and then climbing up a ladder. Things stay the same for a long time, and then you have big changes over very short periods of time. And remember, when we talk about short periods of time here, we're talking about geological time. So for a few thousand years, we see big changes to the populations. What is going to determine whether gradualism or punctuated equilibrium is happening?
The environment.
How quickly the environment is changing. All right, number 9 says, describe directly observable evidence of evolution, including bacteria resistant to antibiotics, weed resistance to pesticides, and natural populations of the pepper moth changing in the forest. So bacteria resistance to antibiotics. We talked about that. Remember, because we used antibiotics so much, it killed off all the susceptible ones. The ones that were left are the ones that were resistant to the antibiotics, weren't necessarily killed by it. Those reproduced, and so the populations got more resistant to it. That is a direct evolutionary change. Something that we've done in a very short amount of time compared to the history of the Earth in the last 70 years or so.
Basically the same thing as if you do an antibiotic.
What's that?
Same thing.
What is the same thing?
Antibiotic.
Weeds, yeah. I mean, just just another example. It's the exact same idea. You're right about that. Exact same idea for the weed and pesticide thing. It's just another case where we see evolution. And then, of course, we talked about the pepper moth and how they changed, the population changed from mostly white to mostly black because of the soot in the Industrial Revolution. And then as those factories got cleaned up and they weren't putting out as much soot and the forests went back to normal, we saw them go back to mostly white. Okay, number 10 says, explain the idea of divergence, geographical, and reproductive isolation. So divergence is where two populations go separate ways evolutionarily. They change in different ways. Remember we talked about the salamanders being separated, and because they were in different environments, they changed differently. And back with the pepper moths, we talked about how the ones that changed were in the forests around London, the ones in the northern forest didn't change. So those populations, we would say, diverged. They changed differently. Okay, geographical isolation is just physically separating two populations. That could happen because they get separated by a mountain chain, or they get separated by a river, or all sorts of things that could happen there. Basically, they are not able to intermix because they are in different parts of the environment. Geographical isolation can lead to reproductive isolation. I guess I should say it's one of the things that can lead to reproductive isolation. But there's other ways that organisms can be reproductively isolated. Okay? So you may have organisms that live in the exact same place, in the same area. They're not geographically isolated, but because one group tends to get out more in the afternoon, and one group tends to get out more in the morning, they're never going to connect with each other. They're never going to intermix with each other. They're not going to find mates in those groups. They'll find them more within their own groups, and they'll be reproductively isolated. Reproductive isolation is anything that means that two groups do not interbreed. Geographical isolation is probably easiest to understand, but there are other ways. And then finally, number 11 says, explain what speciation is. So speciation is when two groups have changed, or at least one group has changed enough that we would consider two groups to be different species. So sometimes evolution can lead to speciation. We end up with two groups that are different enough that we would not consider them to be the same species any longer. Remember, that is not going to happen like that. It's going to be a gradual thing over multiple generations. Yes?
Can I ask a weird question?
Okay.
Okay, it's not really weird. Okay, so dogs are usually set, like, say they're 3, but they're actually like 21. How, like,
Dog eaters is really kind of stupid.
understand that.
It's just a way of going. It sounds weird because we live into our 80s. It sounds weird to us for our dogs to get old and die at 12. So we're going to try to make some sort of weird system so that we can equate their age to ours, but it really doesn't make sense.
So there's no donkeys.
I have a question.
Yes.
We're going to have to know a lot about the phylogenetic species principle and the biological species principle.
Not so much in this chapter. We'll talk about those in another chapter. I just brought those up because we were talking about speciation. We kind of had to talk about what a species is. So I would not worry about those definitions so much right now. Okay, any other questions? not really. The only reason we talked about him is because he realized that there should be a lot more people on Earth. If, I don't know, if people didn't die, basically.
Kill it, spike it.
Why?
Why?
Because being too close to it. Yeah, it was
You know what?
If it stays outside, I will kill it. If it comes inside, it's
He heard you?
killed.
He heard you? No, he heard you.
He didn't respect my
He could have killed her.
Doesn't have to.
He could have been like, oh, yeah, yeah, yeah.
You wouldn't want